Simulation isn't just hard, it is excruciating. Take a single molecule with just 17 heavy atoms. To calculate its properties using density functional theory on a standard Xeon processor, you have to wait 8 hours. Now imagine screening a library of millions of drug candidates. It is impossible. The math scales as O of n cubed with the number of electrons. In 2017, a team at Google Brain asked a radical question. What if we stop solving the Schrödinger equation and start learning it? Deep learning usually relies on structure. Images are fixed grids. Text is a sequence. But chemistry is topology. A molecule is a graph. Atoms are nodes. Bonds are edges. Here is the fundamental challenge. Graph in isomorphism invariance. If I hand you a molecule, the list in atoms is arbitrary. Labeling a carbon as atom 1 or atom 5 changes nothing about the physics. The energy is identical. Standard neural networks, which depend on a fixed input order, break immediately. We need an architecture that sees the shape, not the index.
The authors realized that half a dozen existing models, from Duvernod's fingerprints to Lee's gated graph neural networks, were mathematically identical under the hood. They unified them into a single definition, the Message Passing Neural Network, or MPNN. An MPNN operates in 2 strict phases: the message passing phase, where the graph builds a local understanding of itself, and the readout phase, where that local understanding collapses into a global prediction.
Here is the mechanism. We run a loop for t time steps. Every atom holds a hidden state vector, HV. In each step, 2 things happen. First, the message function, M. Every atom looks at its neighbors and the bonds connecting them to calculate incoming messages. These are summed up to aggregate local information. Second, the vertex update function, U. The atom takes its current state and this new summed message to compute its next state. The paper uses a gated for current unit, or GRU, here. This allows chemical information to ripple across the molecule, hop by hop. After T steps, every atom has a rich vector representation of its chemical environment, but we need a single number for the whole molecule, like its atomization energy. This is the readout phase. We apply a function R to the set of all final node states. The critical constraint? R must be permutation invariant. Whether we sum node 1, then node 2, or node 2, then node 1, the result must be identical. This preserves the physical symmetry we identified at the start. The framework was just the container. The specific architecture matters. Previous models treated bonds as discrete labels, single, double, or aromatic, but atoms exist in continuous space. The authors introduced the edge network. Instead of a static weight matrix, they feed the edge feature vector, containing precise angstrom distances, into a small neural network. This network outputs a dynamic matrix specific to that bond, which then multiplies the neighbor's state. It makes the chemistry differentiable with respect to geometry.
There is a flaw in message passing: latency. In a long carbon chain, it takes many steps for one end to influence the other. To fix this, they experimented with a master node. Imagine a virtual node connected to every single atom in the graph. It acts as a global scratchpad. In every step, all atoms write to the master, and the master writes back to all atoms. This creates a shortcut, reducing the distance between any 2 atoms to just 2 hops, into the master and out to the destination. For the readout phase, simply summing up node states is a blunt instrument. The authors adapted the Set2Set model from sequence-to-sequence learning. Instead of a flat sum, Set2Set uses an attention mechanism. It generates a query vector that iteratively scans the node states, deciding which atoms are most critical for the prediction. It aggregates them into a fixed-size embedding. It is strictly more expressive than summation, yet it remains perfectly order-invariant. To prove this works, they turned to QM9, the standard benchmark for quantum chemistry. It contains 134,000 organic molecules made of carbon, hydrogen, oxygen, nitrogen, and fluorine. Each molecule has 13 physical properties calculated via DFT, ranging from atomization energy to the HOMO-LUMO gap. The goal is not just low error. The goal is chemical accuracy.
This is the threshold where the model's error is indistinguishable from experimental noise. Below this line, the neural network isn't an approximation anymore. It's a replacement.
The results highlighted a crucial engineering trade-off. In cheminformatics, we often ignore hydrogen atoms, treating them as implicit properties of the carbon skeleton to save compute. The MPNN punished this shortcut. When they treated hydrogens as explicit nodes, the graph size tripled, up to 29 nodes per molecule. Training slowed down by a factor of 10, but the accuracy gains were non-negotiable. The precise spatial geometry of those protons was essential for capturing the physics.
So, how did they do? The final architecture, using edge networks, set-to-set readout, and explicit hydrogens, swept the board. It achieved state-of-the-art results on all 13 targets. By ensembling the top 5 models, they pushed the error even lower, hitting chemical accuracy on 11 of the 13 properties. They effectively replicated the results of an hour-long DFT simulation in a fraction of a second, proving that with the right inductive bias, neural networks can learn quantum mechanics.